Hello, for data communications and network one class today, just I will explain about routing in a packet switching network. The packet switching network is still in the topic of the wide area network or WAN. Wide area network. Okay, if you remember. Okay, so packet switching network is the network for WAN, okay? And we will see how we will select the path, okay, to go from source to destination with the routing technique, okay? There are many ways to classify routings techniques, okay? We can use, we can classify based on the who is making the decision, okay? Who make decision. Okay, so I will classify first, okay, based on this concept, okay. So the first one is distributed routing. This is the most common technique, okay. For distributed routing, each node, okay, will choose an output link for incoming packet. So if you have many nodes, okay, in the network, okay, so every node will, like this one receive packet, you make decision which way to go, okay. This one receive packet, it will make decision like which way to go, okay. So each node will make their own decision, okay. The second one is centralized routing. This is an older techniques, okay, of routing, because in the past the computer with very powerful, like computing power is very expensive, so we have like one like centralized like network control center, and all the other node will be like cheaper, okay, the cheaper model, okay. So it will save the cost, okay. So we pay expensive for only one centralized network center, okay. So this one will make the centralized routing. This one will make the decision for everyone, okay. So it's not as robust as the distributed routing, okay. It can fail more easily, because if this center fail, the whole network will fail, okay. So we use distributed routing more because it's more robust, and because the computer is much cheaper nowadays, right? It's very cheap right now, so every node can have the computing power enough to make the routing decision, okay. The third one that we may not use a lot, but it still exists, is the source routing, okay. Think about if you want to go, if you're traveling and you are taking a taxi and you want to go to your hotel, and you tell the taxi that you want to go with the scenic route, okay, to see the ocean, for example, instead of using the least cost routing, instead of using like the fastest route to arrive at the hotel, you want a scenic route, okay, to see the view, okay. So you have like special purpose, so you tell so you make decision, the source will make decision, okay, to tell which way to go, okay, in the network, okay. In the application, other application of sending packets, okay, for example, you may have like military, okay. So station is the one who make the decision, right, not the node. In the military application, if you want to send like important information, secret, okay, information, and you don't want it to go to the public network, then you may specify that it must go in some specific links, okay, cannot go out of this link, cannot go to the public network, okay, to make it more secure, for example. So this can be in a military application also. Okay, now let's classify in another way, okay, in a routing strategy. Okay, we can also classify like routing techniques like static and dynamic, okay. Static means that it's fixed, okay, not changing, so fixed routing is a static routing. Dynamic is like it can change, okay. The fixed routing, this is based on like algorithm, okay. This is kind of algorithm. So you have fixed routing, you have flooding. The fixed routing and the flooding I will explain in details with examples, okay? So I will just not talk too much now. Let's go to the third one. The third one is random routing. You may think, maybe why should we select it at random? Okay, they have some, some use also. Okay, so in this case, the node will randomly pick the outgoing link. Okay, you may have like the same probability of going into any outgoing link except for the one that it received from, right? So if you have many link, okay, so this node make decision, it can go to this one or this one or this one or this one, maybe with the same probability or maybe with weighted probability. Okay, it may more likely to go this way than the other, for example. Okay, but anyway, it's randomly picked, and it will not go to the node that it received the package from. Okay, this is used okay, the difference between this and the flooding. Okay, the flooding, okay, so I have to tell you about flooding a little bit. For the flooding, okay, you have the node like this. Okay, you have to send, okay, suppose you get the packet coming in, you have to send to every link that you connect to. Okay, and if you get this one get the packet, it have to send to every link that is connected to. This one get the packet, it have to send to every link that is received from. Okay, except from the one that it received from. So you will have a lot of copies of the same packet. Okay, but we have also application for flooding, which is emergency. Anyway, it's on the be in another clip. So we have a lot of load, okay, for flooding. But for random routing, you can control the traffic load. You have less traffic than the flooding, okay, because you just randomly pick the route, okay. Example of application I'm searching, actually it has been used for a long time, okay, the random routing algorithm, but this one is application in 2023 paper, okay, is to prevent attack on the low Earth orbit satellite network. Okay, so you know that you have the satellite is one of the important network, okay, that transmit data, maybe broadcasting or important data, okay. So and also internet and everything. So there will be like the hackers, okay, try to attack the network, okay. So if you randomly pick the route that will go out, okay, it will be harder for the hacker, okay, to attack you, okay. So this is one of the application for the random routing, okay, and this is in the publication, you can see in the reference to read more. Okay, next is adaptive routing. Actually, adaptive routing is important, but it's too deep, okay. It's a lot of details, okay, to cover in this class, okay, because we are overview in like all the topics, okay, so we cannot go that deep, and also this one you may, I mean, if you want to know more, okay, you have to kind of search, okay, and study on this topic more. Okay, we will just go over a little bit, okay, to get the idea that each node, okay, will make routing decision based on the current network conditions, okay, and also the type of packets, okay. So current network conditions, okay. For example, if this network is congested in some, if you look at Google Map, okay, and you want to go to some place and they say that this road is congested, you have to plus 15 minutes, okay, it's red, okay, then you may decide to go another way that is blue, and there's no traffic jam, okay. maybe it's longer path, but it will be faster, for example. So you have to have the current network condition, okay? That which one is congested, which one the link is down, cannot go, something like that. So you have to kind of make the least cost routing. The fixed routing will use least cost, okay? But we use the least cost routing algorithm, okay? But on the adaptive way, okay? In the adaptive way, which means that we are getting the current situation and make decision, okay? And type of packet is like if this is high priority and depend on application, okay? Should you select do decide to for this packet to go this way, but this packet to go another way, okay? And this is some examples, okay, of very simple adaptive routing in direct topology. This is from Huawei website, okay? So you have kind of all connected, okay? So the yellow is the shortest path, okay? From this to this, so you have yellow is the shortest path, okay? So usually you will go this way is option 1, okay? But if you have some problem with this link, it's congested or down, then maybe you use this link instead, okay? This is option 2 because it's longer, it's not the shortest path, okay? But you may use it when you have other problems with option 1, okay? So this is kind of adaptive in the easiest way, okay? Now let's go back to the fixed routing. Fixed routing use least cost routing algorithm, okay? You assign the cost to the link and you try to minimize, optimize, okay, the routing the routing, you know, so that you will go there at the destination using the least cost, okay? And we have two algorithms that we will cover, Dijkstra and Bellman-Ford, okay? In this clip, I will cover Dijkstra, and maybe in the next clip, I will cover the Bellman-Ford with examples, okay? The fixed routing is simple. The routes are fixed based on the name, so there's no flexibility, okay? And there is no difference between the datagram and virtual circuit routing because you always take this same route, okay? After you make decision that you go from your home to Kasesa, you always take BTS, for example. So there is no like other options. You always go this way. So if BTS is not working for like half an hour, then you have to wait, okay? Something like that. And so datagram and virtual circuit are the same because all the packet will just follow the same path. Okay, all packet from source destination pair follow the same route or the same path. Now let's look at least cost routing algorithm. Okay, the concept, okay, of least cost routing is very important because virtually all packet switching network is based on the routing decision on some form of least cost criteria. You can set the cost into like actual like money that you have to pay, or maybe the time, okay, like the total time to transmit from A to B, something like that, okay? So usually there's the money and time. These are the two main cost, okay, that we are using. Okay, so each link is assigned a cost based on some criteria, okay? For example, if the number of hop is to be minimized, so each link will have the same cost like 1 unit, okay? Think of it like this. You have okay, hop is like one link, okay? This is 1 hop, 2 hop, 3 hop, for example, from A to B, but this is only 1 hop, okay? This is like you go 1, 2, 3 hops, okay, to B, but this is you go only 1 hop. 1 hop is like 1 link, okay? Think of this as when you're driving and you want to minimize the intersection, you want to minimize the red light, so maybe you don't care that this road is maybe a little bit longer if it doesn't have the traffic light, okay, so or intersection, okay, so you will just which way I will have the fewest number of traffic light. So it's similar to I have the fewest number of hop, because at the node you have to have processing time, right? Processing delay time. So maybe you think that the time to traveling in the link is not much. The processing time or the queuing at the node is more. Okay, so I don't care about the length of the link, but I care about the number of nodes that I have to transit. Okay, so I will just minimize number of hop. Okay, so I will set every link to have the same cost. Okay, so every link have the same cost. So I just count the number of when I added the cost. Okay, I will have if I have minimum cost, I will have minimum number of hop also. Okay, how to assign cost? Okay, usually you have two easy criteria. The first one is that if you have the higher the link capacity is higher, then you give the cost link, lower the cost link. Okay, so think of fiber optics. Okay, fiber optic and wireless. Fiber optics has much more capacity. Okay, much high capacity, right? Low cost per let's say kilobit per sec, which means that for the same data rate, okay, you pay less, okay, because many people share the same fiber optic. Okay, so even though the installation may be expensive, but everyone share, right? So many people share the same link, so for everyone, each of them, okay, it will be cheap to use the fiber optics, okay, to get the high speed. Okay, so this one you assign low cost. Okay, but the wireless think of is like mobile phone that they have to get they have to pay to use the frequency band. Okay, they have to pay a lot of money. The company have to pay a lot of money to get to use the frequency band. So actually the air or the wireless communication is much more expensive to use than the fiber optics. Okay, so this one you assign high cost to the link. This one is low cost to the link. Okay, so if you have this one is fiber, so it's cheap. Okay, this one is wireless, so it's expensive, higher cost, so that everyone will try to send package to the cheaper one. Okay, until if it's congested, there may be some you send to the wireless link, for example. Okay, and also the higher the current load on the link, then the higher the link cost. This is for adaptive routing. Okay, if it's congested, a lot of package going that way already, send you assign more cost, higher cost. Okay, so that some of the package the new coming, okay, may go to different route to lower the load. Okay, so even though the fabric is very cheap, much cheaper than the other link, but not everyone go to fiber optic. Okay, you should have some package go to other routes so that it will distribute the load. Okay, now let's look at the Dijkstra algorithm. Dijkstra algorithm find the shortest path from a given source node to all other nodes. Okay, so if you have the source node like this, A is the source node here, and you have many nodes, okay, in the network. For example, B, C, D, E, F. Okay, so A is the source. So when you do the Dijkstra algorithm for 1 times, okay, that I will show you in the examples in the next slide. Okay, when you do it 1 time, you will get, okay, from source node to every node. Okay, how to grow from A to B, from A to C, from A to D, from A to E, and from A to F. Okay, and then you have to do again. Okay, for B is the source node, and you have to go like B to A, how to go B to C, like this, B to D, B to E, B to F, okay, something like this. And then C is the source node. You have to do it for every node to be a source node, okay. So you have to do this many times, okay. But I show you only 1 round, okay, 1 times of because for every time it will be the same. So let's look at the step. Okay, you increase the length, okay, you develop the part, okay, in order to of increasing part length, okay. We will see at first you may have only 1 link, then you increase into 2 links, 3 links, okay, something like that. Okay, we will see the step quickly, and then we'll look at the examples, and I think you understand more when you see the examples. Okay, now for the step, first we will let set T, okay, is a set of nodes, okay, incorporate so far. So initially set T will include only the source node, okay. At first there was only 1 node, which is a source node in set T. Then you find the neighboring node, okay, that is not already in T, okay, that have the least cost path, okay, from the source node, and then add it into set T. So now T has 2 nodes, okay, the source node and the one other node. And then you update the least cost part, okay, which is the best part at this point, okay. Then you repeat step 3 and 4 until all nodes are in T, in set T. So you go back to step number 3, and then you already have 2 nodes, right? So you add 1 more node, okay, the one that have the least cost path from the node inside of set T. And then you do this and increasing more and more nodes until you include all of the nodes in the network, okay. And this you finish for source node, for 1 source node, like for example source node is A, okay. So you do the whole thing here, you get this answer, okay, and then you have to redo it again, okay. Then you look at examples. Okay, suppose this is given, the node is given like this is the network, okay, and you have source node is 1, is a source, okay. Then you see that there is two-way communication, okay, which is because they have the arrow in 2 directions, so you have two-way communications like this. So you have the cost from 1 to 2 and 2 to 1 is the same, okay, equal to 1. Okay, at first, okay, in the step 1, okay, node T has only source node, okay, so it's actually this one. Then you find the path, the shortest path, okay, to the node, to the neighboring node that is connected to the node in T, okay. So you have, now T has only node 1, so everyone that's connected to 1 is marked like this, and this is the cost. D sub 2 equal to 1, so node 1 to node 2 have cost of 1, node 1 to node 3 has cost of 3, node 1 to node 6 has cost of 6, okay, and node 1 is not connected directly to 4, 5, and 7, so you are not having the link there, okay. Then you think, you look at this, and which one is the cheapest. Node number 2 is the cheapest, it's have a cost of 1. So next you include, okay, you include node number 2 in the set. So you have 1 and 2 like this, okay, and D2 is still 1, okay. Then since you include node number 2 here, you can have more connections, okay. So you have node number 1 and number 2, so now node number 4 is connected to node number 2, so it can be included because node number 2 is already in set T. So node number 4 is included in node number 2, connected to node number 2. So you have a connection from the set T, okay, to number 4. The others, node number 3 is the same, node number 6 is the same. You have another one is node number 5, okay. Node number 5 have D5 equal to 3 because now node number 5 connected to number 2, okay. Node number 5 here connected to number 2. So when you have number 2, you can have, this line, okay, extra line, okay, here. So it's connected. So now you have extra node D4 and D5 here. Which one is cheapest? Okay, so you have node number 3 has cost of 3, node number 5 has cost of 3. Okay, I will include the number 3 first, but actually you can include both, okay, at the same time. You will get the same answer. But for the exam or for the test, please do it step by step, okay? Because it will be easier to make mistake, okay, when you skip the step, okay? And in the program, okay, they usually do it. They have to do it step by step also. Okay, so in the third step, okay, we include only node number 3 here. So I have 1, 2, 3 here. Now node number 4 is changing. Instead of connected to node number 2, because I have node number 3 now, I connect node number 4 from node number 3. Now my cost become 4. Previously my cost of node 4 is 5, right? But I connected from node number 3. Now my cost is 4. Okay, the other number 5 is the same, number 6 is the same, but I have extra number 7 because node number 7 can connect to node number 3. So if 3 is in the set T, then I have node number 7 here as a possibility. Okay, then which one is cheapest? Node number 5, okay. So now I have 1, 2, 3, and 5 here. And the connection is changing, okay. 5 to 7 is changing, the others are the same. And I see, okay, then I have number 4 and number 7 the same cost. I'm adding number 4 first, okay. So I have step 5, I have 1, 2, 3, 4, 5, and the other connection is the same, okay. Then step 6, I have T include 1, 2, 3, 4, 5, 7, okay. Now it's changing that number 6 instead of before we have 1 to 6, right? But now we have 7 to 6, okay. 7 to 6 is cheaper, okay. The cost become 5 instead of 6, okay. Before we have this, and the cost is 6, but this one we have cost of 5. So we select this one, and this is our answer. This is the last step. T include all the node, okay. So this is the end of the Dijkstra algorithm. Okay, you must be careful. The important point, okay, so this is the source node, right? Source node. So every node coming out, the direction coming out of the source node. So only one direction of the arrow, okay, because this is the path to go, okay. And 1, 2, 2, 1, 2, 3, 1, 2, 3 to 4, 1, 2, 3 to 4, 1, 2, 2 to 5, 1, 2, 2 to 5 to 7, 1, 2, 2 to 5 to 7 to 6. This is the path to go to every destination, okay. And there must be no loop, okay. There must be a tree. Answer must be a tree. Answer of the Dijkstra algorithm, okay, must be a tree and must have no loop, okay. If you have a loop, what does it mean? If you have a loop, it means like you can go like from A to B. You can go this way or can go this way. This is a loop, okay. So you cannot have this because there's more than one way to go from source to destination, okay. and your answer must be wrong, okay, because there must not be any ambiguity of which is the best path to go, okay. So you must have no loop, okay, important. Answer must be a tree, no loop, okay. Okay, so this is the Dijkstra algorithm examples, and we will cover the other algorithm in the next clip, okay. This is reference that I'm trying to make it like more updated, okay. And this is the applications of the random routing. You can search, okay, and from many sources, okay, because they are talking about routing. Search from many sources, update your information all the time, okay, in this field, okay, and compare information from many sources, read from the updated information and from many websites or books or papers, okay, and it helps you understand more, okay. Thank you.